Work done by a torque on the rigid body. Consider a rigid body rotating about a fixed axis, say z axis. All the particles of the rigid body other than on the axis describes circle in a plane perpendicular to z axis. One of such particles is described displaced a displacement ds1 under the action of force F1 in time delta t. The angular displacement of the particle is d theta. The work done by the force on the particle is dw equals to F1 dot ds1. F1 ds1 cos phi 1 equals to F1 ds1 cos 90 minus alpha 1 equals to F1 ds1 into sin alpha 1, equation 1. Because in triangles CP1 P1 dash d theta equals to ds1 by r1, ds1 equals to r1 d theta, hence dw1 equals to f1 r1 d theta sin alpha 1 equals to r1 f1 sin alpha 1 into d theta. Question 2. The torque on the particle about origin tau1 equals to OP1 cross F1 or equals to OC1 plus C1 P1 cross F1, OC1 cross F1 plus CP1 cross F1 or top perpendicular plus tau Z or equal to CP1 cross F1 or symmetric body value of OC1 cross F1 comes out to be 0. This implies tau1 equals to CP1 cross F1 equals to R1 cross F1. Mode of tau1 equals to mode of tau1 equals to R1 F1 sin alpha 1 n cap equals to R1 F1 sin alpha 1, equation 3. Hence from 1 and 2 dw1 equals to tau1 d theta. Top perpendicular torque on the particle perpendicular to z axis, tau z, torque on the particle along the z axis. The situation is shown. Here this is theta and d theta af1 and it is theta 1, here it is alpha 1, it is phi 1, this is ds1, so d theta 1 equals d theta equal to ds1 by r1 we have used. Now if there are another forces acting on the body, then the total work done on the body will be equal to the sum of the work done by these forces. Hence dw1 hence dw equals to dw1 plus dw2 plus dw3 dash 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 equals to tau1 d theta plus tau2 d theta plus tau3 d theta plus dash 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 equals to 100 by tau1 plus tau2 plus tau3 dash 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 into d theta, because d theta is for same for all torque. This implies dw equals to tau into d theta, equation 4. This is the expression for the work done by total external torque acting on the body rotating about a fixed axis. Dividing equation 4 on both sides by dt, we get dw by dt equals to tau into d theta by dt. Or this implies P, that is power, equals to tau into d theta by dt equals to omega, angular velocity, tau into omega. This is the expression for instantaneous power of a rotating body, where P is the power, tau is the torque, and omega is the angular velocity. In a perfectly rigid body, there is no internal motion. The work done by external torque is used to increase the kinetic energy of the body. The rate at which work is done Work done on the body is equal to the rate of increase of kinetic energy. Thus dw by dt equal to d by dt, and rotational kinetic energy is given by 1 by 2 I omega square. Dw by dt equals to power equals to 1 by 2 I is constant, 1 by 2 is constant out of differentiation, and d omega square by dt. This implies since power equals to tau into omega equals to 1 by 2 I, and differentiating it q omega into d omega by dt. This implies tau omega equals to I omega into alpha. Omega omega is removed, so tau equals to I alpha. The tau is the torque, I is the moment of inertia of the body, and alpha is the angular acceleration. Thus, external torque produces angular acceleration in the rotating body, and this is equivalent to the linear force. That is, if we write F equals to ma, where F represents force, mass, m is mass, and a is extension in rotated. In the case of rotation, torque equals to I into alpha, where I is moment of inertia and alpha is the angular acceleration. That is, F is equivalent to tau, tau is equivalent to F, I is equivalent to m, and angular acceleration is equivalent to linear acceleration. Now, angular momentum in the case of rotation about a fixed axis. Consider a rigid body of mass m rotating about a fixed axis, say z axis. Consider a ith particle of mass mi at a point q. The position vector of the particle is ri, and linear velocity is vi. Here you see that the position vector is ri and linear velocity is vi. Hence, linear momentum of the particle is pi equals to mi into vi. Now, angular momentum of this particle about origin, Li vector equals to Ri cross Pi. This is from formula, we know that L vector is equal to R cross P. So, Li vector equals to Ri cross Pi vector. We are calculating the angular momentum about origin. Now, Ri is here Ri represented by OQ vector, and this OQ vector can be written as sum of this vector plus this vector, that is OCI plus CIQ. OQ vector is equal to OCI vector plus CIQ vector. So here we have written OCI cross CIQ vector cross PI vector equals to OCI across R perpendicular I vector, because this CIQ vector is perpendicular distance between Q and axis, Z axis, so it is written R perpendicular I. So R perpendicular now taking cross product in both OCI cross PI plus R perpendicular I cross PI vector. Hence, angular momentum of rigid body about origin, angular momentum of the rigid body, total angular momentum, then L vector will be summed over all particles, that is sigma I equals to n OCI cross PI plus sigma R perpendicular I cross PI vector. Now this is written as R perpendicular plus this is written as RZ vector, L perpendicular plus LZ vector, where L perpendicular component of angular momentum perpendicular to the fixed axis, and LZ is the component of angular momentum whose direction is along fixed Z axis. So now LZ vector equal to sigma R perpendicular I cross PI vector equals to sigma R perpendicular I cross MI VI vector equal to sigma R perpendicular I MI VI sin 90, since R perpendicular and V vector are perpendicular to each other. So taking cross product, we have sin 90 k cap. sigma r perpendicular I f by r perpendicular I into omega, because v equals to r omega, so we use k cap, or equal to sigma mi r perpendicular I square omega into k cap. Now sigma mi r perpendicular I square into omega k cap, or equals to I omega k cap. Hence L vector equals to L perpendicular plus I omega k cap. Question 2. This thus in general direction of L vector is not along z axis. Now for a symmetrical body which is symmetric about rotation axis, for a given OCI vector, for every particle which has a velocity vi vector, there is another particle of velocity minus vi vector located diametrically opposite on the circle with center Ci described by the particle. Together such pairs will contribute 0 to L perpendicular vector, and as a result for symmetric bodies L perpendicular is 0. Hence for symmetric body equation 2 becomes L vector equals to I omega k vector k cap, I omega k cap equals to Lz vector. So we have L vector equal to L perpendicular plus Lz equals to L perpendicular plus I omega k cap. We know that tau vector equals to dl by dt. This implies tau vector equals to d by dt L perpendicular plus I omega k cap, dl perpendicular by dt plus d I omega by dt into k cap. For a symmetric body rotating about symmetric axis, hence L perpendicular is 0, so dl perpendicular by dt equals to 0. The stop vector equal to di omega by dt into k cap, or equals to I d omega by dt k cap, equals to and d omega by dt equals to alpha, that is acceleration, rotational acceleration, angular acceleration, equals to I alpha k cap. In magnitude tau equals to I alpha. That is torque equals to moment of inertia into angular acceleration. Now conservation of angular momentum. We know that tau vector equals to dl vector by dt, that is differentiation of angular momentum is torque vector. If external torque is 0, that is tau vector equals to 0, then dl by dt equals to 0. This implies dl perpendicular by dt plus dlz by dt equals to 0. This implies dlz vector by dt equals to minus dl perpendicular by dt. Now for a symmetric body rotating about symmetric axis, L perpendicular is 0, hence dl perpendicular by dt equals to 0. Thus dlz vector by dt equals to 0. This gives Lz vector equals to constant. This implies I omega k cap equals to constant, or this implies I omega equals to constant, or I1 omega n equals to I2 omega t. Why the angular speed of the girl sitting on a swivel chair reduces when she stretches her arms horizontally? This is a situation where the principle of conservation of angular momentum is applicable. If friction in the rotational mechanism is neglected, there is no external torque about the axis of rotation of the chair, and hence I omega is constant. If stretching the arms increases the I about the axis of rotation, resulting in decreasing the angular speed omega.